Welcome to the February edition of the McKinney Amateur Radio Club monthly meeting. The date is February 13th. I hope you all know that you're supposed to be here because we want you here. Let's do the Pledge of Allegiance. Hey, I hit the button. There we go. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. So with that, I'm going to give it over to Larry so he can do a quick introduction of our presenter, and thanks, everyone.
Thank you very much. Ladies and gentlemen, who wants to know about impedance? I know a little bit about it. I had to study some of it. Ever since I was a kid, you get to looking on speakers and whatever, and it says something about impedance being 8 ohms. Okay, 8 ohms. I know what an ohm is. I got an ohm meter, so I can measure it, right? I don't think that's exactly right. And we're fixing to find out what the whole deal is here. Ladies and gentlemen, please give a warm welcome to our member, Dr. Tim, or Dr. Tom Kim. Thank you very much for coming out. Hope that microphone works all right for you. Do you need both microphones?
Yes.
Yes. Need both? Oh. Okay. Oh, gosh. It sure is. Well, thank you. It's important that you hear me, not necessarily see me. Okay, the topic is transmission line impedance real, and where did the power go? These are two related questions, as I hope to reveal to you soon. Next slide, thank you. We'll have a brief introduction, give some examples of common transmission lines, some commercial coax examples, and then try to develop the relationship of electromagnetic field theory, which all of our radio is based upon, to transmission line description. And we'll use that description to calculate the characteristic impedance and the propagation factor. Those are two related quantities that we want to take a look at. And then finally, I'll give some numerical examples of power lost in coaxial transmission lines, and then close it with some summary and conclusions. Next slide, please. Well, as we all know, transmission lines are the RF arteries of our systems. We want maximum radiated power on transmit, and we want to receive the maximum power. Transmission line performance parameters are impedance and power loss, or attenuation. We're going to look at that. Practical transmission lines are low loss, but they're not lossless. Otherwise, we couldn't use them. We're going to identify the causes of propagation loss on transmission lines, and then take a look at the impact of load reflection coefficient as it affects the power loss. And then finally, a brief statement about the cost of transmission lines and something for you to consider for your station. Next slide, please. Some common transmission lines, the ever-present coax, consisting of two conductors, an inner cylindrical conductor and an outer cylindrical conductor, generally filled with dielectric. Then there's the open wire or ladder line that uses air as the dielectric. And then transmission lines that are used mainly in integrated circuits, microstrip and shielded microstrip. And you often find those in digital radios. But we're going to focus on coax in this talk. Next slide, please. I believe it's over 2 years ago that W3LPL gave MARC a presentation on his HF antenna farm. And there's a photo of some of his 9 towers. I think only 7 are illustrated in this photo. But the remarkable thing is these towers are 150 to 180 feet tall. So if you combine that with the distance between the tower bases and the shack, that is a long transmission line run. Obviously, low loss transmission lines are needed. Next slide, please. Not to belabor the point, but N6WIN in Arizona has towers that are 145 feet tall. And closer to home, there's a tower on Preston Road in Prosper. Some of you may have seen it. And I estimate that with those 6 Yankees that are on there, it's probably 80 to 100 feet tall. So there are some tall towers around, and people need low loss transmission lines. Excuse me while I get a drink of water. At my age, my throat dries out very quickly. Next slide, please. This slide is from a page of the DX Engineering Coax. These are all nominal 50 ohm coax. And I say nominal because with manufacturing tolerances, even though they're supposed to be 50 ohms, it varies a couple of ohms. In the rectangular red boxes below each one, I don't know if you can see it or not, but this says attenuation per 100 feet. And it gives the attenuation versus frequency. So it goes from 5 megahertz in this case up to 450. This is equivalent to an LMR 400 coax. The one I've circled over here is what I call cost-effective coax. It's RG8X. It's one I use because I have a relatively short run at my shack. Again, you can see the attenuation per 100 feet numbers versus frequency. And a column that you may be wondering about, this efficiency number, all that is the efficiency that corresponds to the same attenuation in dB. So for example, 1 dB loss is about 80% efficiency. Next slide, please. This is some more expensive, but very, very good cable. Heliax, this is 1/2-inch heliax. And for example, even at 30 megahertz, even at 50 megahertz, less than 0.5 dB per 100 feet. Very, very good coax. Comparable one is the RFC or LMR 600, also very good coax. These numbers are a little smaller to see, but I think at 50 megahertz, it's about 0.55 dB per 100 feet. Next slide, please. Why is most coax 50 ohm impedance? Well, back in the 1930s, Bell Telephone considered transmitting phone voice messages over coax long distances with high power transmitters. And so they asked a couple of Bell Labs staff to investigate power handling versus and loss versus coax impedance. And they did that, and they found that minimum loss in coax versus impedance was about 75 ohms. But power handling maxed out at about 30 ohms. So guess what they did? They compromised. Modern coax is filled primarily with polyethylene, which has a relative dielectric constant of 2.2. And it just so happens, serendipity, that the minimum loss is at about 50 ohms. So 50 ohms is a good choice and is used as a standard coax impedance in network analyzers and all kinds of stuff. Next slide, please. By the way, are you all hearing me okay? Okay, good. In the 18th and 19th century, there were 3 critical experiments that were performed that founded the basis for electromagnetic theory. Coulomb conducted experiments that demonstrated that electrical charges exerted forces on each other, and that led to the definition of the electric field. Ampere conducted experiments with electrical current loops and demonstrated that they exerted forces on each other, and that led to the definition of the magnetic field. And Faraday conducted experiments with time-varying magnetic field in and out of a loop of wire and demonstrated that voltages were developed. And that was Faraday's magnetic induction. Well, Maxwell, a very smart guy, studied all of those experiments and started to formulate what we call electromagnetic field theory. And he did a clever thing. He looked at what Faraday did and he said, I wonder what would happen if I included a term in Ampere's equation that would correspond to a current that corresponds to the time-varying electric field. And lo and behold, when he did that, he developed equations that predicted that electric and magnetic fields could propagate as waves. And that's key. In 1894, a self-taught physicist and mathematician, Heaviside, simplified Maxwell's numerous equations into about 8 that we use today, and conceived of a lumped element transmission line circuit model. And we're going to look at that in a little bit, using inductance, capacitance, resistance, and inductance per unit length. And oh, by the way, he invented Coax. In 1888, Hertz demonstrated radio wave propagation. So transmission line analysis is based on EMT, electromagnetic field theory. Next slide, please. I said we're going to focus on Coax tonight. So in this box, these are the lumped element parameters that field theory has calculated for us in terms of the parameters of the coaxial line, in particular, the inner radius of the inner conductor and the radius of the outer conductor, A and B. And as you can see, the inductance per unit length, capacitance per unit length are dependent upon those. This is magnetic permeability, and we take it for free space, which is mu0, it's just a number. The other is epsilon prime, that's the real part of dielectric constant. But those are the numbers that you can use to calculate per unit length the inductance and capacitance of this coaxial line. The parameters that are circled here, R and G, are the villains tonight. Those are the characters that are responsible for loss. We're going to look at that in a moment. But notice that the conductor resistance per unit length is related to this quantity R sub S, and R sub S is in turn related to 1 over this squiggle, which is the Greek delta, and it is called skin depth. And we're going to talk about skin depth in a moment. G, the conductance per unit length, is related to another funny squiggle with a double prime on it. And this turns out is the dielectric loss term. We're going to look at that in just a moment. But we note that these element values that we're going to use in the transmission line circuit are geometry dependent, and we're going to find use for them very, very soon. But first, we're going to take a look at these two terms, R and G. Next slide, please. Skin effect. Skin effect for RF fields is a result of the electrical current crowding in this perimeter going into the conductor roughly a couple of skin depths, delta. And it turns out that the electric and magnetic fields are 0 inside the conductor. They only reside outside of this conductor. And as a result, as delta gets smaller, for example, if frequency increases, then the skin depth gets smaller and smaller, and the conductor resistance gets bigger and bigger. So as frequency goes up, the conductor resistance increases, you got more I squared R losses. And as an example, at 14 megahertz, I hope I didn't move that too close. At 14 megahertz, the skin depth is less than 1/1000th of an inch. So it's pretty tiny. But nevertheless, this is what contributes to R in the transmission line equivalent circuit. Next slide, please. Okay, I'm going to try to slow down on this one a little bit. In a dielectric, if there's no external RF field applied, the electrons in the molecule of the dielectric more or less are symmetrical around the center charge, positive charge, and they're symmetric. But when this field is applied, it tends to push the electrons and they displace. And what it does, it creates a little electric dipole. So what happens is these nearest neighbors, when the fields are varying, they tend to agitate the molecules and they give up heat. It's just like current flowing through a conductance or a resistor. So that's effect is described numerically by this epsilon double prime. So epsilon double prime accounts for the dielectric loss in our equivalent circuit that we're going to take a look at. Next slide, please. So this is Heaviside's circuit model. Consists of R and L for the conductor and G and C for the dielectric. The relevant circuit equations are given over here, just ordinary circuit analysis, represent the voltage drop from the input to the output and the current change from the input and the output. Now, we said that electric and magnetic fields are waves. The voltage and current are proportional to E and H directly. And so since the electric and magnetic fields are waves, so are the voltage and current. So if we substitute an expression that represents a voltage wave into these equations, we find that the propagation factor is equal to R plus J omega L times G plus J omega C, that whole thing to the square root. And the characteristic impedance is R plus J omega L divided by G plus J omega C, again to the square root. When we look at these, we realize that these are complex numbers and they are both calculated from our lumped equivalent circuit model. Next slide, please. In order to evaluate those, it's helpful to compare R over omega L and G over omega C because it simplifies those expressions. And when we do that, we find that R over omega L is much smaller than unity and G over omega C is much, much smaller than R over omega L. So let's proceed to the next slide and see what that does for us. When we look at it, here's the original expression we had for characteristic impedance. If we define Z0 as being the square root of L over C, and what we've done is we pulled J omega L and J omega C out of this square root. This is the expression that we get, and this is the same one that we had from field theory analysis on L and C, and you plug that in, you get this equation for Z0. This is the lossless characteristic impedance term. But we see that Z sub C is complex because it has both that term and then this other term that depends upon R and G. And I assumed Z0 of 50 ohms using some numbers to calculate for RG8X and find that the reactance term in the characteristic impedance at 14 megahertz is about 0.3 of an ohm. So it's about 6% of the characteristic impedance. So yes, Z sub C is complex, but the reactive component is so much smaller than the real part that it's practical to assume that the characteristic impedance is real. But note that when R is equal to 0 and G is equal to 0, that reactance goes to 0. So again, it reinforces our understanding that without the conductor loss and the dielectric loss, the characteristic impedance would be real. Next slide, please. We do a similar thing to evaluate the propagation constant. It turns out that it breaks out into a real and I'm going to say an imaginary term. It's not imaginary at all, just means a phase shift. But this is a familiar phase constant that we see quite often. If we think about transmission line and we ask, is the physical length and the electrical length the same? The answer is no. It's because it's filled with a dielectric, and this reflects that effect. Again, note that alpha accounts for a decreasing amplitude of V and I, and you'll see that more clearly in the few slides to follow. But again, when R and G are zero, the attenuation factor goes to zero. Again, it becomes a lossless line. But for us, we're faced with the fact that indeed it's not zero, and we can't neglect it even for low loss lines, especially if we're fortunate enough to be running 300 or 400 feet of coax somewhere. Excuse me. Next slide, Sean. Just wanted to give you a sort of an image of what the exponential decay is because of loss. You see a sine wave. When there's no loss, the amplitude stays constant. But when there is loss, then the amplitude begins to decrease, and it goes as this factor e to the minus alpha x, where alpha is that attenuation factor and x is the distance. So this is the way our traveling waves will behave on a real transmission line. Next slide, please. Okay, this is a busy slide. In general, we have both forward and backward waves on transmission lines because very seldom are our transmission lines perfectly matched. And anytime that there's a termination on the line that has an impedance other than Z sub C or Z0, you're going to get a reflected wave. In fact, thank goodness, because that's how our antenna analyzers work. In red are shown the forward voltage and current waves, and you notice they propagate with this propagation factor that has both the attenuation and the phase factor in it. And the backward waves likewise behave in the same kind of fashion. The ratio of the forward voltage wave to a forward current wave is equal to the characteristic impedance, as is the ratio of the backward voltage wave to the backward current wave. So at any point, let's say minus x1 on a transmission line, the net voltage at that point is the sum of these two waves. And the same for the current. It's the sum of the two current waves. So since we know gamma, we can relate these voltages at this point to the voltages and currents waves at this point because of the knowledge of gamma. And we also can evaluate the impedance at this point as the ratio of V to I. And in terms of the forward and reverse traveling waves, we obtain that expression. So it allows us to relate voltage and current waves at any line position to another line position, and we can evaluate impedance. Next slide, please. Okay, so let's consider the terminated lossy line. We connect an impedance at x equals 0 to this line. Using the results on the previous page, we can express V2 and I2 in terms of these quantities. In addition, we can form the ratio of the reflected wave voltage amplitude to the forward voltage amplitude at x equals 0. And we define that as the reflection coefficient. And in terms of the load impedance and Z0, it's this expression, ZL minus Z0 divided by ZL plus Z0. So if ZL is equal to Z0, there's no reflection. Gamma is 0. So if we have an incident power in terms of the forward traveling voltage and current waves, at this particular interface, we can calculate what goes into the load. It's the incident power minus the reflected power. And now we're using the definition of gamma sub L. So the load power, which is the difference of those two, is given as 1/2 V plus squared. That's it, at X equals 0 times 1 minus gamma squared divided by the characteristic impedance. And that's the incident minus the reflected power. That is the load power. Okay, let's go to the next slide, please. Knowing that, as we said before, we can calculate the impedance to the input of the line. And that impedance, if we use that, we can calculate the power from a source that is connected to that line. And the power that is delivered to this network then has to go only two places, either into the load or into the line. So this expression, Pin is equal to P line plus P load, will be used in the following numerical examples. Next slide, please. These are the 4 coax that I used for comparison. I did it at 14.2 megahertz, variable line length of 0 to 300 feet, and assumed that the input power was 100 watts. And what we're going to look at is the power loss on the transmission line. Next slide, please. So the first is the matched line case. These were the specifications that were given on the DX engineering page when they gave you the attenuation per 100 feet. That was a matched line case. And so, for example, we might have an antenna at the end of our transmission line, and Dave brought his hairpin matching element so that our Yagi is looking around 50 ohms. So we have no reflections on the line. So if the source sends a wave, a forward wave down the line, that wave and that power will undergo one-way line loss, which is e to the 2 alpha L, where L is the length of the line. Next slide, please. Okay, so now we're going to look at some numerical results for the four types of lines. I compared my cost-effective line with Heliax. At 300 feet, RG8 or DE8X dissipates over half the power, about 52 or 3 watts out of 100 goes into the line. In contrast, Heliax, it's about 15 watts. Next slide, please. LMR 400, it's about 28 watts. The SMC 600, under 20 watts. So it's pretty good, pretty good. Next slide, please. Now, this is where the plot thickens. We'll let the reflection coefficient be something other than 0. So I chose 2 values, 0.36 and 0.68. And now for my low-cost line, the loss is increased to about 58 watts, but at less than 300 feet, about 250, it's already dissipating 50 watts, half of the power. And at reflection coefficient of 0.68, it's even worse. Next slide, please. Heliax, still pretty good, even at 0.36, less than 20 watts on the line dissipation. And even with this corresponds to an SWR of about 5 to 1. The line loss is just a little over 30 watts, not too bad. Next slide, please. LM400, not too shabby, a little over 30 watts at 0.36. And yeah, not too great at 0.68, almost half the power. Next slide, please. LM600, looking pretty good. A little over 20 watts at 300 feet and about 34 watts at 300 feet when the reflection coefficient hits 0.68. Next slide, please. So this is just a replot of some of that data. This is the power loss at 300 feet versus the load reflection coefficient. And for all the lines, you can see as the load reflection coefficient increases, so does the line power loss. Next slide, please. And here's the oh, by the way. This is my cost-effective RG8X. These prices may have changed. I think I found these a year or two ago. It could be a little more now. Heliax is pretty expensive. The SM600, not bad. It's expensive, but not bad. Okay, next slide, please. All right, to summarize, obviously transmission lines are essential. We have to have them. Electromagnetic theory is the basis for transmission line analysis and description. We can use lumped inductance, capacitance, resistance, and conductance to describe the characteristic impedance and the proper propagation parameters. Yes, to be exact, the characteristic impedance is complex. However, the reactance term is small enough that we can consider it real. And the reactance term is dependent upon R and G. And if R and G are zero, as we said before, then the characteristic impedance would be real. R and G do affect the loss on the line, and we can't neglect them. 50 ohms is the standard coax impedance, as we stated before. And the attenuation per 100 feet is a key parameter when comparing. Next slide, please. Long TI runs require small attenuation factors. I think that's obvious. Larger reflection coefficients result in larger power loss. Matching minimizes the reflected power at the load and should be used whenever possible. I like my cost-effective coax for lengths less than 100 feet. Heliax obviously is the very best for long runs, but it is expensive. And I would say LMR 600 or SMC 600 is a good choice at moderate cost. And one more slide, please. Just wanted you to know that there is an online calculator by AC6LA. It's called TL Details. You input a number of parameters, including your selection of coax, your frequency, the load that is terminating the line, and it will calculate both the load power and the power lost in the line. And that's it. Thank you.
Yeah, I think there's going to be questions now. Yeah, I hear them asking already.
Yes, Dick. Yes.
So where would something like ladder line fit into this whole thing? Because it's supposed to be less lossy.
Yes, it is less lossy because it,
Repeat the question.
oh, okay. The question is, where would ladder line fit into this? And because it's less lossy, I think is your, yes, it is. However, it is susceptible to other stuff being close to it. That's a great advantage of coax, is self-shielding. So as long as you don't encourage any of the currents that are inside to go out and flow down the outside of the conductor, you're in great shape, because the fields can't penetrate a good conductor, as we saw before. Good question. Yes, sir.
Two questions. First one, skin effect. Is that skin effect on the shield, or is that on the core of the coax?
It's on both. Great question. If we zipped back, Sean, to the, keep going back. Yeah, there we go. We'll go forward one more, or back, I'm sorry, backward one more. There. You notice R is dependent upon 1/A plus 1/B. The first is the resistance of the skin effect on the inner conductor, and the other is the skin effect on the outer conductor. You're right. Thank you for pointing that out. And
I guess my second question is, in the computer world, we usually say you can only go as fast or as good as your slowest component, however, right? Is mixing, let's say you have a feed line that you're mixed matching with, let's say, RJ58 in your shack, but then the main line is going to like LMR 600. Is there a big difference that even if it's like less than 10 feet or something like that, or?
I mean, you'd like to use one kind of coax, but it's 50 ohms. And you want to transition into another kind of coax, but also 50 ohms. In principle, that should work. The question is, at those connectors, you could have some shunt reactance that you might have to tune out. It depends on how it's done. If the transition can be made very gradually, then you should not encounter a problem. It depends upon the design, but it's an excellent question. Thank you. Yes, sir. Yes. No. Propagation, good question. What's the difference between propagation factor and velocity factor? I'll take the easier one first. Velocity factor is the ratio of phase velocity in the dielectric to the phase velocity in air. Since the dielectric has a larger dielectric constant, it slows the wave down. So a given physical length of line is longer electrically because you get more variations because the phase velocity is slower in that line. Good question, though. And there was another part. What
Propagation.
Oh, the propagation factor includes both the phase factor that we just talked about, as well as the attenuation factor. So it's both those numbers that go into that propagation factor. Any other questions? Yes, sir.
Yeah, I noticed when you were showing the loss curves
Mhm.
that all of those curves looked like they were starting to flatten out. Is there any point when you continue graphing it out that it flattens completely?
I would say that if you extended the line to infinity, which
Point taken. So if our announcements, got a big one on this slide. We're going to start out with the two easy ones. Number one, we have the MARC information net every Sunday night at 8 o'clock on the 2-meter repeater. Please make sure that you join if you can. MARC Simplex net every Monday night, 8:30. Our friend Robert here tends to that net, and is, from what everything I hear, has been doing an awesome job of keeping everybody engaged. Simplex nets are, I want to say, relatively new. They're not relatively new to the club. We've had it around for a while, but they haven't been well attended. What I'm hearing is we're starting to get a lot more attendance. We're getting people outside of the club on the nets, which I think is awesome. So it really helps raise the profile of the club, helps us all to better understand how to do simplex stuff, especially at VHF frequencies, which is not something that a lot of our, especially our newer hams, have done a lot of. So I think this is a good deal. Now for the big announcement. We're making a change this weekend. We're going to try a new venue for our weekly breakfast. We are moving to the IHOP, which is directly across 75 from us here in this building. So we will be meeting there between, people generally tend to show up anywhere between 6:45 and 7, well, Brands at 7:30 on the dot. So people start showing up about 6:45, and as long as you get there by 7:30, the waiter or waitress will be able to take your order. Come on out, man. We get a pretty good crowd. I think this last Saturday we had 23 people for breakfast, which is good because we knew that there were like 3 or 4 of our regulars that weren't even there. So if if some of those regulars had been there, we might have set a new record. But yeah, it's a really great gathering. People, the conversations run the gamut from things like transmission line loss to what's a great show to watch. So it kind of matches what's going on Discord, but face to face. Okay, that all being said, is there a motion to adjourn? Got Lance with the motion, second by Steve. Any discussion? All in favor, say aye. Any opposed? Thank you, everyone, for coming. It was a good meeting.